Happy day students. In this class we are going to learn about heat, internal energy and work. So what is meant by heat? Already we discussed about heat in last class, right? So what is meant by heat? Heat is a form of energy which occurs or which flows from one body to another body when there is a temperature difference. Okay, so heat is a form of energy. It flows from one body to another body. When it flows from one body to another body, if there is a temperature difference in between those two bodies, right? So it depends. Heat energy is going to be denoted with Q. So Q is directly proportional to the mass. If mass is more, then heat energy is also more. Okay. If mass is more, heat energy is also more. Okay. That's about simple heat. Okay. Now internal energy. What is meant by internal energy? So there is a block. So in this block there are many particles are there or molecules are there, atoms are there, like whatever it is. So these particles are in initially random motion. So these particles are having some energy. That energy will be called as internal energy. That means this internal energy is going to be denoted with capital U. So internal energy U equal to sum of kinetic energies plus sum of potential energies. So this is called as internal energy. So internal energy is sum of kinetic energies as well as sum of potential energies. So when we will have kinetic energy, when we will have potential energy for this, these particles or molecules or atoms have in motion, if they are always in motion, random motion, that will be called as kinetic energy. So kinetic energy may be translational, vibrational and rotational kinetic energies. Okay, then what about potential energy? Potential energy is nothing but it is the interaction between these two molecules. If there is interaction, what interaction? Molecular interaction. Okay, if the molecular interaction is there, then there is a potential energy. If there is no molecular interaction, then it have only kinetic energy. So kinetic energy is translational, vibrational and rotational. Three will be there. Okay, now so if this gas, so this gas will be called as real gas. The gas which is having both kinetic energy as well as potential energy has internal energy, that will be called as real gas. If it has only kinetic energy, that means there is no interaction between the molecules, then that will be called as ideal gas. That gas will be called as ideal gas. Okay, got it? So this is for real gas internal energy. For ideal gas, this is the potential energy. Okay, clear? Right. So we'll see some important points regarding this. At absolute zero, that means at zero temperature, the translational kinetic energy is also zero, but the matter has still internal energy due to vibrational motion and rotational motion of number of atoms within the molecules is called zero point energy. That point will be called as zero point energy, where at zero, at absolute zero temperature. At absolute zero means where it is at 0 Kelvin. Okay, at absolute zero temperature means it's at 0 Kelvin, not 0 degree Celsius. Okay, so at 0 Kelvin, the translational kinetic energy is 0. What is the formula for kinetic energy? It's a 3 by 2 kT. Here temperature is 0, so this total term will be 0. But the matter has still internal energy, because internal energy consists of translational kinetic energy and vibrational kinetic energy and rotational kinetic energy. So here initially still molecules are there. These are in vibrational motion and rotational motion. So it has internal energy. Okay, so that energy is called as zero point energy, where kinetic energy, translational kinetic energy is 0. That point will be called as 0 point energy. Okay, and as well as it depends what it is. Internal energy depends on the parameters like pressure, volume, temperature, moles. It depends on the system, how it goes, how it increases, that's also will be increases. If decreases, it depends on the thing. For a given gas, either real gas or virtual gas, translational kinetic energy depends only on its absolute temperature. So 3 by 2 K T. Okay, T is the absolute temperature. Okay, so it will be 0 only. Okay, right. So absolute internal energy of the system is not measurable, but change in internal energy means du. So du can be measured easily, but absolute internal energy it's not possible to measure. So we can measure internal energy of the system. Okay, Next, when the temperature of the system increases, for example, here is a system is there, here there are molecules or particles are there. Now I am increasing the temperature of the system. What will be happen to the internal energy? Your molecules will go with fast, no? Speed will be increases. When the temperature increases, velocity will be increases. When the velocity of the each molecule increases, then what will be happen? Kinetic energy will be increases. When kinetic energy will be increases, what will happen to the internal energy? It is also increases. If temperature decreases, velocity of the molecule decreases, kinetic energy of the molecule decreases, then internal energy of the volume also decreases. When it is increasing, the change in internal energy is positive. When it decreases, the change in internal energy is negative. And when it remains constant, when temperature is at constant, okay, let's consider at 0, then change in energy is 0. Okay, change in energy is 0. Got it? Right. So now let's see. So this is about internal energy when it will be changes at constant and these things. Now we'll see there is this point du means change in internal energy depends. Let's take a p v. P means pressure, v means volume graph, pv graph. We'll discuss about pv graph little later, just take it as like an example. So pv graph, let's consider a point a and there is a point b. Okay, so this is the starting point and this is the ending point. So this, at this point it has initial pressure, at this point it has final pressure. Okay, clear? So now I can do some work. I am giving some energy. This is the initial state, this is final state. So from here to here I can do the work in three process. One will be in this direction, and one will be in this direction, and one more will be in this direction. So let's consider three works. Here this work done W1, this work done W2, this work done W3. Okay, three work done. Okay, so at this point three work done means three have different kinetic energies. Already we discussed heat energy is directly proportional to mass. Okay, so three things we are taking. So three have different masses or same mass also, no issue. But if the work is differ, then kinetic energies also differ. So W1 Q1, W2 Q2, W3 Q3. Okay, so when it moves from there to here, initially its work is W Q1. Now the work done is W1. So Q1 minus W1 is an internal energy of this path. Okay, now W2 Q2. That means Q2 minus W2. Q2 is the first point, W2 is the final point. Then Q3 minus W3. See these 3 points are same only, no? This is the point. At this point W1 Q1, W2 Q2, W3 Q3, right? So points are same. That means, so it depends only on the initial and final points. Initial and final point. Initial, final, initial, final, initial, final. But see the paths. This is different path. This is different path, and this also different path. So that means it is independent of the path followed by the system. Okay, it depends only final energy minus initial. Final is Q, initial is W. That means final is heat energy, initial is work done. Okay, got it? Right. So that means very important point. Change in internal energy depends on initial and final points of the states. States means this state, this point. That means where the pressure, volume, that points will be called as state. Okay, state of system. Clear? And it is independent of the path. Whatever the path it will be, it can come. Okay, clear? So in this path, okay, we'll discuss this again later. So internal energy will be positive when it may be positive, may be negative, or maybe 0. Temperature of the system increases positive, temperature of the system decreases negative, and it remains constant, then it will be 0. Okay, this is about internal energy. See next, work done by an ideal gas. For example, let's consider a container filled with a gas. So this is the gas which is filled inside. Okay, initially its pressure is P. Okay, now consider this gas is an ideal gas. Now this area, this total area of cross section is A. Okay, and let's consider because of this gas here there will be some pressure will be created. Okay, because of that force will be acting on this point, so that this wall or this piston will move to this point, will move to this point. That means let's consider this distance is some dx, small x. Okay, clear? Dx it will be changes. Initially this is the position, now it changes to here. That is distance will be dx. That means it's done some work, right? To move from here to here, there is some work has done, right? That is nothing but work done. Work done equal to force into displacement. Okay, work done equal to force into displacement. Similarly, what about pressure? Pressure equal to force by area. So from this force equal to pressure into area. This pressure I am going to replace there. Work done equal to pressure into area into S. S is nothing but distance. What distance? Dx distance. ADX is nothing but ADX is nothing but change in volume. Okay, there is a change in volume. If it's expanding, no, expanding means there is a change in volume, right? Got it? Right. So work done is nothing but power into change in volume. So here pressure is, sorry, not power, pressure. So pressure is a constant, delta V is a change in volume. Very, very, very important formula. When pressure is constant, this is the formula. If pressure changes, if P is constant, if P is constant, work done equal to power into change in volume. That will be written as P into V2 minus V1. If P varies, if P varies, work done will be written as integral volume from V1 to V2 P dV. Okay, it will be written as P dV. Volume is going to change from V1 to V2. This is the volume V1, now the volume is V2. Okay, so this is during expansion. Gas is expanding. Which gas is expansion? Ideal gas is expanding. Here we are considering all over, we will consider only ideal gas. Okay, W equal to integral V1 to V2 P dV. Okay, clear? Right. As the gas expands from V1 to V2, the temperature is also going to be increases, right? So when the temperature increases, for ideal gas constant, PV equal to nRT, where P is the pressure, V is the volume, N is number of moles, R is real gas constant, and T is temperature. Okay, clear? So this will be written as, when volume changes, work done is also called as W equal to PdV, right? W equal to PdV. That will be equal to nRdT. If you want to write W equal to P delta V, then this will be written as nR delta T. Okay, that means P of V2 minus V1 equal to nR T2 minus T1. Clear? So simply change in work will be written as P of V2 minus V1, or the change in work is also written as nR of T2 minus T1. Okay, clear? So this is about simple work done. Now we'll see the graphs regarding this. So now there is the PV diagram. PV diagram. So here on x-axis volume will be taken, on y-axis pressure will be taken. Okay, clear? Right. From this, if first condition, if P is constant, it will goes in this direction. That means it's expansion only. Okay, P is constant, so it is going to changes from volume V1 to volume V2. So here, what about this? What we will call this and all? This is called as area. Okay, here pressure is constant. If pressure is constant, what is the formula? Work done equal to P dV. If varies, W equal to integral V1 to V2 PdV. This is for constant, this is for varies. Which is varying? P is varying, pressure varies. Okay, right. So from this area, it is like a square. So what is the formula for square? That side into this side. What is this side? P. This total is P. This side is V1 to V2. So work done equal to P of V2 minus V1. Final volume minus initial volume. So this is the work done. Then when what will be happen when it will be changes? V1 to V2 integral of P dV. Okay, understand? Right. We will discuss about this little later again. So this is for now. That is W equal to P V2 minus V1. If here what's happening here, it is expanding that, so that volume is increasing. If it compresses, so same pressure volume, it compresses at same constant temperature. Now this will be a position of V1 and this will be the position of V2. So work done equal to P of V1 minus V2. Which is greater here? V1 is greater or V2 is greater? V2 is greater. Okay, so that means this value will be negative. So here work done is negative. Okay, here work done is negative. Here work done will be positive. That means when it is expands, when it expands or along right side, work done is positive. Along left side or contracts, work done is negative. Okay, clear? Right. Here we will see another same pressure volume. If the pressure decreases like this, pressure changes. Before constant, right? Now it changes. So here pressure V2, here pressure V1. Sorry, V1. Here pressure is P2. Here pressure is P1. So let's consider small area here. This is varying pressure, no? And when the pressure is varies, what we have to take? Small elements. Small elements will be taken. This small element is dx, or sorry, dv. So that it will be written as W equal to integral P dV. From where to where the volume is changing? V1 to V2. So we need to find individual work and we need to sum of this from where to where V1 to V2. Okay, clear? So what is this area? This total area will give what it will give? Area under PV graph. Area under PV graph gives work done. Okay, so if it is along this direction, it is positive. In this direction, it is negative. Here what is happening? V1 to V2 is volume is increasing or decreasing? Increasing only, no? That means this is the direction. So when volume is increasing, what will be happen? Then this will be taken as positive. Okay, if the graph will be P V, the graph is being like this, like this. What about this? This is also coming down only, no? Coming down means work done positive or negative? Positive. So this is also positive, this is also positive. Clear? Right. Then when it will be negative? If the direction is from A to B, it is moving like this, but in opposite direction. That means this is V2, this is V1. So it is moving from V2 to V1. V2 to V1 means volume is decreasing. That means it is contracts. When it is contracts, work done will be negative. Okay, clear? Right. So the total work done will be the total area which it occupies. And here is also total occupies. So simply what we are understanding very clearly here, work done will be positive when it is in this direction or this direction or what? Look here and tell me. In this same direction it is positive, opposite direction negative, same direction in this direction, what will be? It's also called clockwise. Clockwise positive. Left side means anti-clockwise, then that is negative in this direction, or it is anti-clockwise. So work done is positive in clockwise, work done is negative in anti-clockwise. Okay, clear? Understand? Then can you tell me which is having more area? I'll mention the two paths here. So A, B. So this is one path and this is another path. This is another path. So which is occupies more area? Same pressure, volume graph. So this total area is for A to B in this path. Let's consider that is W1. So W1 is there. Now what about this one, this area? This area means this is the area which is occupies, right? That is W2. So which is greater? W1 only greater. Okay, clear? Work will be greater. But what about internal energies? Internal energies, change in internal energy is 0. There is no change in internal energy. So at this point internal energy, at this point internal energies are equal, du1 du2. Okay, clear? But work done will be greater when work done is positive. When it is negative, it will work done will be decreases. Clear? Understand? So let's take one small example here. There is a gas, there is an ideal gas which is in a container of it's going to be its volume. Initial its volume is 10 liter. Now it is expands so that its volume increases to 20 liter. Okay, at a pressure of 2 atm, 2 atmospheric pressure of gas is there inside. Okay, let's consider it is ideal gas. It's a constant pressure. Okay, at a constant pressure. So what will be work done? So here what is constant? Pressure is constant. When pressure is constant, work done equal to PdV. From where to where it is changing? 10 liters to 20 liters. So what about pressure here? Pressure given, pressure equal to 2 atmospheric pressures. So P equal to 2 into 1 atmospheric pressure means 1 atm equal to 1.013 into 10 to the power of 5 pascals. Okay, so this will be written as 1.013 into 10 to the power of 5. So it will be 2.026 into 10 to the power of 5 pascals. So this is the total pressure which is there, and this is volume V1, this is volume V2. So this is given in liters. You have to convert it. 1 liter equal to 1 liter equal to 10 power minus 3 meter cube. Okay, 1 liter equal to 10 power minus 3 meter cube. So what about V1? V1 equal to 10 into 10 power minus 3. V2 equal to 20 into 10 power minus 3. So this will be 10 power minus 2 meter cube. This will be 2 into 10 power minus 2 meter cube. So what about work done? Work done equal to pressure dV. So W equal to pressure is 2.026 into 10 to the power of 5 into dV. dV is 2 into 10 power minus 3 minus 1 into 10 power minus 3. So that means 2.026 into 10 power 5 into 2. If we will take 10 power minus 3 common, then it's a 2 minus 1. So it is 2.026 into 10 power 3, 10 power 5, here 10 power 3, 10 power 5 minus 3, 10 power 5 minus 3 is 10 power 2 joules. Okay, 2.026 into 10 power 2 joules. Okay, sorry, here it's 2, 2, it's also 2, then here it will be 10 power 3 joules. Okay.